Modern chemical plants, oil refineries, and offshore platforms operate under extreme, constant stress. They manage highly pressurized pipes, volatile hydrocarbons, and temperatures high enough to melt steel. Look at this densely packed control room. You are seeing the brain of the facility. This is the Basic Process Control System, or BPCS. Operators use the BPCS to manage daily operations, constantly tweaking heat, pressure, and flow rates to keep production running at maximum efficiency. But if a temperature gauge breaks, a valve jams, or a hacker breaches the network, the BPCS fails. The highly pressurized chemicals escape containment, leading directly to a catastrophic blowout. When the primary control system is compromised, or outright causing the disaster, operators cannot rely on that exact same system to safely stop the resulting fire. The facility needs an independent way to shut itself down. That is the role of the Safety Instrumented System, or SIS. It acts as the facility's ultimate, uncompromisable last line of defense. The core philosophy of an SIS is absolute separation. The primary network manages operations, while an isolated, dormant safety network sits alongside it. It only monitors danger thresholds. If a tank overheats, the SIS wakes up, physically cutting the primary network off from output valves. To guarantee operational safety, energy companies build a multi-million-dollar auto-ocean infrastructure whose sole purpose is to ruthlessly override the primary production line. The architecture of an SIS breaks down into three distinct physical stages. First are the dedicated safety sensors, independently monitoring variables like toxic gas or pipeline pressure. Those sensors feed data into the second stage, the logic solver. This is an independent, highly ruggedized computer hub that evaluates the sensor data against strict safety thresholds. To prevent false alarms, the logic solver uses voting. If one of three sensors spikes, it waits. When a second agrees, it triggers an alert. The signal fires to the final control elements, heavy-duty valves that immediately snap shut to choke off the process. From the exact moment that second sensor trips to the time the heavy steel valves lock into place, this entire sequence executes flawlessly in milliseconds, entirely without human intervention. Deciding exactly how strong this shutdown sequence needs to be involves a mathematical framework called LOPA, or Layer of Protection Analysis, which calculates a facility's specific hazard risk. Risk reduction is categorized into safety integrity levels, from SIL 1 for modest risks to SIL 4 for extreme hazards. As we move up, the allowable probability of failure drops exponentially. SIL 3 requires redundant hardware to ensure the probability of failure is effectively zero. Integrating this strict math creates a modern engineering dilemma. Plant operators need to view the SIS data on their daily screens, but connecting the safety system to the main network introduces a cyber vulnerability that threatens its required digital segregation. An SIS is a mathematical guarantee that extreme physical risk has been engineered down to a tolerable probability. This brings up a strange maintenance paradox. An SIS is a vastly expensive, highly complex system whose success is defined by doing absolutely nothing for years at a time. If a system never activates, it becomes incredibly difficult to mathematically prove that it isn't broken. To maintain reliability, operators are bound to the safety lifecycle, a relentless, mandated regimen of physical proof testing and calibration. Without rigorous physical testing, gradual sensor drift or a mechanically sticky valve will silently create a dangerous, undetected point of failure. Industrial safety is never achieved simply on the day a system is installed. It is an active, decades-long mathematical commitment to vigilance, working in the shadows to guarantee that tomorrow is just another boring day.